All right, moving on to chapter 6, we're going to start with the periodic law, which states that the properties of the elements are periodic functions of their atomic number, meaning every so often in terms of atomic number, so many increase in atomic number, we get to elements that have similar properties. For example, the noble gases, they differ by atomic number between helium and neon, 8, neon and argon, 8, argon and potassium, 18. So we see this repeating pattern. That's what periodic means, repeating pattern. For the noble gases, they all have a valence configuration of Ns2Np6, except for helium, of course. N is the principal number, or energy level or principal level, which makes them generally unreactive. Not that all of the noble gases are unreactive. Some of the more massive ones can form compounds with either oxygen or fluorine. Some of the other parts of the periodic table, make sure you're familiar with these terms, the representative elements. These are the S and P block elements, and this does include the noble gases. So another name for the representative elements are the main group elements. And so when we talk about the trends in the periodic table, it will refer primarily to the main group or representative elements. We also have the transition metals, which are the metals in the D block, so groups 3 through 12. Those make up the transition metals. The F block elements are called the inner transition elements. On top we have the lanthanides, and on the bottom we have the actinides. Letter E, very important, the outermost or valence electrons have the greatest influence on the properties of the elements. Adding an electron to an S or P sublevel has a dramatic effect on the chemical and physical properties, but adding an electron to D or F sublevel does not have such a great effect. Same thing applies when you remove an electron from an S or P sublevel compared to removing an electron from a D or F sublevel. So it's the valence electrons that we're most concerned with. And again, when we get to the periodic trends, we'll be talking about those electrons specifically. So let's take a look at the periodic trends. Here are some of the factors affecting the properties of the elements. Our first one listed there is effective nuclear charge, ENC, or Z effective, which is the charge that valence electrons experience is less than the actual nuclear charge due to shielding of the inner shell or core electrons. Let me reword this. The outer electrons, their attraction to the nucleus is partially blocked by inner electrons, and so they don't feel the full strength of the nucleus because of that. And so this is known as effective nuclear charge. This idea that the valence electrons are less attracted to the nucleus as you increase the number of core or inner electrons. This is known as shielding effect. Number 2, the principal level that valence electrons are located affects the properties of an element. The higher this value is, two things. One, the greater the energy the electron possesses. So remember that electrons that are further from the nucleus have more energy. And secondly, as I just talked about with effective nuclear charge, the smaller the attraction the electron has for the nucleus. Again, this is not due to just shielding, but sheer distance from the nucleus. As distance from the nucleus increases, the attraction between the nucleus and the valence electrons decreases. Now, this is known as Coulomb's law, where it shows the factors that affect attractive forces. We'll talk more about that later on. Another factor to consider when we're talking about the trends of the periodic table is the magnitude of the positive charge of the nucleus, which is due to the number of protons within it. So we'll talk about nuclear charge, which is the charge of the nucleus, which is determined by the number of protons inside of the nucleus. Sometimes, too, we have to look at these things called inter-electronic repulsions. The prefix inter means between. So the electrons in an atom, because they have like charges, they're negatively charged, will repel each other. And this is just a phenomenon that's observed. Like charges repel, opposite charges attract. Now, this will only be an issue when we're comparing elements in group 15 to those in group 16, or when we're looking at negative ions, especially when we talk about ionic radius, negative ions compared to other atoms or ions. And one more factor that we need to sometimes consider is the sublevel that the last electron is placed in. So this will be important for both ionization energy and electron affinity. It says this is an issue when comparing elements in groups 2 and 13 or those in groups 12 and 13. And again, we'll see some examples for each of those. So the first three are things we always want to look at, especially here in number 2, the energy level the valence electrons are located in. We also often are going to look at number 3, the magnitude of the charge of the nucleus. And then 4 and 5 are sometimes things to consider. So these are primarily, with the exceptions to the trend, we'll look at intra-electronic repulsions or the sublevel that electrons are being added to or removed from. So let's start with the trend in atomic radius. Now, you will have to explain why these trends exist. So don't just memorize the trend. Make sure you understand both parts of the trend. So this is 2 parts. We have a group trend and a period trend. So it says in number 1, atomic radius increases as you go down within a group or family. This is because the electrons are in higher and higher energy levels, or those, again, it's the valence electrons we're concerned with, or the valence electrons are in shells that are further from the nucleus. If you take a look on page 223, just take a couple elements to compare. Let's compare lithium and sodium. Pause the video if you need to turn to that page. Lithium has an atomic radius of 1.52. I believe these are in angstroms. And then the atomic radius of sodium is 1.86. Potassium 2.27. So we see this trend. As you go down within a group, atomic radius increases. So keep in mind that lithium, for example, has its valence electron in the 2nd energy level. Sodium has its valence electron in the 3rd energy level. Potassium has its valence electron in the 4th energy level. So these electrons, valence electrons, are found further and further from the nucleus as you go down within a group. Number 2, atomic radius decreases as you go from left to right across the period. For example, beryllium has a smaller atomic radius than lithium. Well, think about what lithium and beryllium have in common. They both have their valence electrons in the same energy level. Same thing with sodium and magnesium. They have their valence electrons in the same energy level. So what's the difference? What's different between, say, sodium and magnesium? In this case, it has to do with nuclear charge. So magnesium has a greater nuclear charge than sodium. Magnesium has 12 protons in its nucleus. Sodium has 11 protons. So with that increase in nuclear charge, the electrons, especially those valence electrons, are more strongly attracted to the nucleus, and so they are pulled in closer to the center, giving magnesium a smaller atomic radius than sodium. So make sure when we're comparing nuclear charge, you do say that whatever you're comparing have their valence electrons in the same energy level, and then nuclear charge is a reason for the difference in atomic radius. So you can see that's all the way across. We're just showing the main group elements, so S elements in the S block and P block, and we're not going to worry about those in the D block, the transition metals. For ionization energy, let's start off with the definition. Something to keep in mind. Remember that the electrons in an atom are attracted to the nucleus. And so ionization energy has to do with removing electrons. Anytime you separate things that are attracted to each other, that requires energy. So look at the definition. First, ionization energy is the minimum amount of energy that is required to remove an electron from 1 mole of gaseous atoms. So take an element, turn it into a gas, and we're talking about removing an electron from a mole of those gaseous atoms. Second ionization energy is the energy required to remove a second electron from an atom. Should be noted that successive ionization energies increase, meaning it is harder to remove the second electron than it is the first. It's harder to remove a third compared to the second electron, harder to remove the fourth compared to the third. So each electron that you remove from an atom, or in this case an ion, as you remove electrons, gets harder and harder and requires more and more energy. So trend in ionization energy. Ionization energy decreases as you go down within a group, opposite that of atomic radius. Again, electrons are being added to higher energy levels, further from the nucleus, weaker attraction to the nucleus, therefore easier to remove. Ionization energy increases as you go from left to right, again, opposite of atomic radius. This is not a coincidence. As you go left to right, nuclear charge increases, the attraction between the electrons and the nucleus increases, and therefore it is harder to remove or requires more energy. So again, we can see this in the book, table 6-1. If you look at lithium, sodium, potassium, rubidium, let's say, the ionization energies all decrease as you go down. So you're removing electrons that are further and further from the nucleus, or less and less attracted to the nucleus. And we see as you go left to right, ionization energy increases. So magnesium has a higher ionization energy than sodium. Again, that has to do with a higher nuclear charge, stronger attraction between the electrons and the nucleus. Figure 6.2 shows that there are some exceptions to the trend. And these exceptions are important. So if you look in any period, most notably the second and third period, when we get to the fourth period elements, you have d electrons, and that really changes things up a little bit. So we'll focus primarily on the elements in periods 2 and 3. And we see there's a couple exceptions. So the general trend, as atomic number increases, so does ionization energy. We see a little dip in period 2 at boron, and we see a little dip at oxygen. Likewise, in period 3, we see a little dip with aluminum and a little dip with sulfur. So here are the exceptions to the trend, group 13 compared to group 2. So just like boron and beryllium, we would expect boron to have a higher ionization energy than beryllium because of its higher nuclear charge, but it does not. Why not? It has to do with what sublevel the electron is being removed from. I'll show you in just a second. We also see a little dip or decrease in ionization energy when we're comparing elements in group 15 to 16. Again, we would expect, say, oxygen to have a higher ionization energy than nitrogen. It does not. Why would we expect that? Well, oxygen has a higher nuclear charge, but it does not have a higher ionization energy. This has to do with inter-electronic repulsions. So let's do this. I'm going to show you with orbital diagrams why these exceptions exist. So let's examine the valence shell for beryllium and boron. So I'm going to go ahead and circle the electron that would be removed from beryllium. Now be careful, don't mix up the exceptions. Sometimes students will say, oh, beryllium has a lower ionization energy because more inter-electronic repulsions. Well, beryllium does not have a lower ionization energy, it has a higher ionization energy. Let's then take a look at boron. When you remove an electron from boron, where does it come from? Which electron of the 3 valence electrons is the easiest to remove? Now, thinking back to the photoelectron spectrum of, say, something like boron, that 2p electron is in a higher energy sublevel. One of two things. First of all, it is easier to remove an electron from a higher energy level. It's easier to remove an electron, say, from sodium than it is from lithium. It is also easier to remove an electron from a higher energy sublevel. So the 2p sublevel is a higher energy sublevel than the 2s. So because you're removing an electron from a higher energy sublevel, boron has a lower ionization energy than beryllium. It's easier to remove an electron from boron than beryllium. So that trend exists all the way down anytime we're comparing an atom in group 2 to an atom in group 13. So that would also be the case for magnesium and aluminum, calcium and gallium, but again, it gets a little messy there with all those d electrons. Let's look at the other exception. So here are the orbital diagrams for the valence shell for both nitrogen and oxygen. First of all, we would expect oxygen to have a higher ionization energy. because though they both have their electrons in the same energy level, second energy level, oxygen has a higher nuclear charge. We would expect that the electrons then in oxygen are more strongly attracted to the nucleus, but that is not the case. Oxygen has a lower ionization energy. So why is that? So let's take a look first at nitrogen. Which electron from nitrogen is the easiest to remove? Well, those 3 electrons in the 2p sublevel are degenerate, meaning they have the same amount of energy. So it takes the same amount of energy to remove any one of them. So I'll just circle the last one. When you remove an electron from oxygen, which one is the easiest to remove? It's not going to be any one of the 4 electrons in the 2p sublevel. See in that first orbital that there's a pair of electrons? You have 2 electrons in the same space, near each other, close to each other. Those electrons are going to repel. They're going to push away from each other, and it's going to make it easier then to remove one of those electrons. So oxygen experiences greater interelectronic repulsions than nitrogen, giving oxygen a lower first ionization energy. Now make sure you use the word greater, because all electrons in all atoms repel each other. So every atom experiences interelectronic repulsions. In this case, oxygen has a lower first ionization energy because it has a greater amount of interelectronic repulsions. Go ahead and take a look at example 6-2 on page 227. We're comparing ionization energies of sodium, magnesium, aluminum, and silicon. What they all have in common is they all have their valence electrons in the 3rd energy level. So the general trend, as nuclear charge increases, so does ionization energy. But I think we have one of those exceptions there. So it looks like we have an exception between aluminum and magnesium. We would expect aluminum to have a higher ionization energy. But because aluminum's electron that is being removed comes from a higher energy sublevel, the 3p, it has a lower ionization energy than magnesium. So we go sodium, aluminum, magnesium, and then silicon. Go ahead and turn to page 246 and take a look at number 25. This is a very common question. So we're given successive ionization energies required to remove each of the electrons from an atom. So what we want to look for, just like we talked about with the photoelectron spectrum of an atom, we want to look for big jumps in energy. So that big jump is going to tell us something about where the electrons are located, whether we're removing inner electrons or valence electrons. So go ahead and pause and see if you can answer that question. Did you get boron? So what this tells us is that this particular atom has 3 valence electrons. So the first 3 ionizations are fairly close to each other, not too far apart. But then we see a big jump from IE3 to IE4, about 10 times. IE4 is about 10 times greater than IE3, which tells us the 4th electron that is removed is not a valence electron, it is a core electron, and will require significantly more energy to remove than the first 3. Next up is electron affinity. This is kind of the opposite of ionization energy. Look at the definition. The amount of energy released. So you're adding this time an electron, and energy is released in the process. So ionization energy, you're removing an electron, that requires energy, endothermic. Adding an electron to an atom is exothermic. That process releases energy. So just think of it as adding an electron. Don't worry too much about the actual definition, especially in terms of energy. Electron affinity decreases as you go down. So it's harder to add an electron far from the nucleus than it is close to the nucleus. Again, you're trying to get this electron that's negatively charged to stick to the atom. That's more likely to stick if you're adding that electron close to the nucleus where the attraction is strong than far from the nucleus where the attraction is weak. Electron affinity increases as you go left to right. Again, same reasoning that we talked about before. So as nuclear charge increases, it's easier to add an electron. There's going to be a stronger attraction between the nucleus and that added electron. Like ionization energy, there are some exceptions to the trend. The exceptions are found in group 2 compared to group 13. So it just says group 2 there, but compared to group 1 compared to group 2. as we'll see in just a second. And then we also see an exception to the rule when looking at group 15 compared to group 14. 14 to 15, 1 to 2. And I'll show you examples in just a minute. So take a look on page 228. Graph looks a little funny because energy is released, so it's shown as a negative value because it's exothermic. We see at the very bottom of the page some other values instead of in a graph and a periodic table. We see the general trend is electron affinity increases as you go up and increases as you go right. Before we do any examples, again, let's look at the exceptions to the trend. So when comparing elements in group 1 to group 2, so let's compare sodium to magnesium. So again, this idea here is we're adding an electron. The electron will be added to the valence shell. So I'm going to show in a different color where the electron goes. So when you have a sodium atom and you add an electron, it's going to go into the 3s sublevel. And again, don't worry about interelectronic repulsions here because this is not what's going on. When you add an electron to magnesium, that electron is going to go to a higher energy sublevel, the 3p sublevel. It is easier to add an electron to a lower energy level. Likewise, it is easier to add an electron to a lower energy sublevel. So even though magnesium has a higher nuclear charge, because the electron being gained goes in a higher energy sublevel, magnesium has a lower electron affinity. So be careful with that one. So it's easier to remove an electron from a higher energy sublevel, ionization energy. It's harder to add an electron to a higher energy sublevel, electron affinity. Let's look at the other exception to the trend. So here are the orbital diagrams for the valence shell for carbon and nitrogen, group 14 and group 15 elements. Take a guess. When you add an electron to carbon, where's it going to go? Well, it's going to go in that empty p orbital. When you add an electron to nitrogen, where is it going to go? Notice that nitrogen's p sublevel contains 3 half-filled orbitals. So adding an electron is going to go into one of those half-filled orbitals. So what's the problem with that? Well, by adding an electron to an already half-filled orbital, this increases the amount of interelectronic repulsions. Those electrons don't really want to be together. And so this gives nitrogen a lower electron affinity. Again, we would expect it to have a higher electron affinity due to its higher nuclear charge. But in this case, we have an increased amount of interelectronic repulsions when you add an electron to an already half-filled orbital in nitrogen than adding an electron to an empty orbital like in carbon. So take a look at example 6.3 on page 229. It says the range of following elements from most negative, that means highest, to least negative electron affinity. So highest to lowest electron affinity. So we're comparing potassium, bromine, cesium, and chlorine. So potassium and cesium have their valence electron, or the same number of valence electrons, different energy levels. Potassium and bromine have their valence electrons in the same energy level. Chlorine has its valence electrons in a lower energy level than any of those other atoms. And then we have cesium has its valence electron in the highest energy level. So when we arrange things from highest electron affinity to lowest, chlorine having its valence electrons in the lowest energy level will have the highest electron affinity, followed by bromine. Bromine is higher than potassium because bromine has a higher nuclear charge, and it is not one of the exceptions. Cesium has the lowest electron affinity because its valence electron, or where you add an extra electron, is going to go the furthest from the nucleus, therefore resulting in the lowest electron affinity. Go to page 246, question number 31. And let's do all parts, A, B, C, and D. Go ahead and pause the video, please. So we're going to skip B because that's group 4. It's a transition metals, but it's the same as A. So electron affinity increasing as you go up within any group. Letter C increases as you go left to right across the period, in this case, period 2. And then for those elements, lithium, potassium, carbon, fluorine, and chlorine, it goes in this order increasing. So potassium has its valence electrons in the highest energy level and has a relatively low nuclear charge, and therefore it's going to have the lowest electron affinity. Fluorine has its valence electrons in the lowest energy level, relatively high nuclear charge, and so it will have the highest electron affinity. I'm going to pause at this point. I will make a second video with the last couple periodic trends, just so we're not having such a long video. All right, thanks for watching.